So in your reading this week, you're going to read about periodic trends. And there is a lot there that you could just memorize, but I really want to discourage you from doing that, because if you can understand why these trends are the way they are, then they become really easy to remember and you don't have to sit there with a table trying to memorize it. So what we're going to do is I'm going to go through these concepts, because if we understand what's happening with that, then all of these trends, which I'll talk to you about, will make a lot more sense. So I'm going to start with talking to you about some of this stuff up here. You'll notice what I've made on the side here has kind of just my little snippet of the periodic table. So here's our regular periodic table, and then off to the side, I've made some Bohr models of a couple of atoms I've selected. So I've pulled lithium, sodium, fluorine, chlorine, and neon, and I've kind of placed them sort of where they are in relationship to each other on the periodic table. So I've got kind of why I have them set up like this. So the reason I have the hydrogen show you where we're at in the periodic table, because then you can compare one atom to another. So you'll remember from our previous lessons that the periodic table has what we call periodicity, which means that as we go from one row to the next, we start repeating patterns. And so lithium and sodium are in the same column. They're both in the first position of the row. Remember, columns are vertical, rows are horizontal. So they're in the same position in the row as the first thing. And when we do their electron configuration, we know that this means that they end with some number S1. And that's going to be the reason that they have similar characteristics. So let's talk about each of these things as well. So we remember that opposites attract and like charges repel. That's going to be really important when we're thinking about our periodic trends, because inside our nucleus, we have a positive charge, a dense positive charge, and then these electrons have a negative charge. So as we move throughout the periodic table, the more protons we have, so the higher our atomic number, the more positive charge we have, and therefore the more attraction we have between the protons and the electrons. So the protons and the electrons are always attracted to each other, and the more protons we have, the more they're attracted to those electrons. So that's one of the pieces we'll have to think about when we think about these trends. But with that in mind, the other piece we have to think about is a phenomenon called shielding. So shielding is where we have these extra energy levels that kind of diffuse the attraction between the positive and negative. So imagine you have a positive magnet. This is like our nucleus, right? And then you have a negative magnet here. There's a big attraction between these two. But if I was to put another negative magnet here, then these guys would feel the attraction the most, but this one would feel it a little bit less. So this is kind of how our in-between energy levels are acting between the nucleus. So then we can imagine this is one energy level of electrons here, and then this is on the next energy level of electrons. So between those energy levels, there's going to be a stronger attraction on the inner energy level electrons as compared to the outer ones. So the more energy level shells we have, the more shielding we have between these outer energy level electrons and the nucleus. And then the last thing we want to think about is that atoms, I'll leave that there actually. I think that's helpful. Atoms are most stable when they have a full valence. So when they have a full s orbital and a full p orbital. We're not going to really think about the d orbitals for the purposes of our class. So if we look at neon, for example, neon is a noble gas, and its electron configuration is 1s2, 2s2, 2p6. It has filled the 1s orbital, because the s orbital can hold 2 electrons, and it's filled the 2s orbital, which can hold 2 electrons, and it's filled the 2p orbital, which can hold 6 electrons. So it has 8 electrons in its second energy level, 2 in the s, 6 in the p, and so it's very stable. It's got all the electrons it wants. If I compare that to lithium, lithium only has 1 electron in its second energy level. So it's far from stable, because in order to be stable, it would need either just these two in the 1s, because then it would have a full outer energy level, or it would need all 8 in that second energy level to be stable. With fluorine, if we look in the second energy level, in order to be stable, we would have 8 electrons. We would have 2 in the 2s and 6 in the 2p. And so if we just had one more here, then it would look like neon and it would be stable. So if we have a good understanding of all 4 things listed here, that opposites attract each other, that there's periodicity based on where that electron configuration brings us, that there's shielding between energy level layers, and that atoms are most stable when they have a full valence, if we understand all 4 of those, then we're in a really good position to not have to memorize these trends and to just understand why they are the way that they are. Oh, okay. So let's talk about them. So atomic radius is the size of an atom. It's just how big it is. And as we move across the periodic table, our atomic radius, pull my picture up, my atomic radius is going to change based on, if I have more energy levels, you can see, compare lithium to sodium, I have more energy levels, and so the further out I get, the more orbitals I've got, the bigger my atom is going to be. So as I move down the periodic table, because of these additional energy levels, my atomic radius is going to increase, meaning that these atoms on the lower part of the periodic table are going to have a bigger radius. They're going to be larger atoms than the ones at the top of the periodic table. So I'm going to put my first trend on here. So this is atomic radius, and what I mean in drawing this arrow is that atomic radius increases as you move down a periodic table, meaning this is going to be bigger than this. So if someone was to ask you which likely has a bigger atomic radius, potassium or sodium, potassium is K, then you would say probably potassium. There are exceptions to all of these rules, but we're just going to think of them as the trends in general. Now, as we move across a period, so across the period table, across a row, period and row mean the same thing. So as we move across a row, what we see is that there's actually, because they have the same number of energy levels, so they've got the same number of shells, but there's more protons in this nucleus, and there's more electrons with the same amount of shielding. So what's happening is that fluorine's nucleus is going to pull more on those electrons. That attraction is going to be stronger between these guys than it is between these guys, because there's the same amount of shielding. There's only one energy level between the nucleus and the outer energy level. So there's the same amount of shielding, but there's a bigger positive and a bigger negative than there is here. So because that pull is stronger, this is actually going to get squeezed together. We can imagine them just squeezing into each other. And so this, even though it's got more protons and neutrons and electrons, this is actually going to be smaller than this guy. Because again, same amount of shielding, but larger disparity in charge. That's also going to be true for neon. I'm just using fluorine because when I think about my trends, I tend to think about them only including this part of the periodic table, and then I think of the noble gases kind of as their own thing. But for this case, this is also true including the noble gases. So this guy would be even smaller because we're still moving across. So here I'm going to draw my arrow in this direction. So as we move across a period, atomic radius is decreasing, meaning that these are going to be bigger than these. All right, so our next trend that we're going to talk about, so we've done atomic radius, got that. Our next trend is ionization energy. What ionization energy refers to is the amount of energy that it takes to pull away one electron, to get rid of one electron. So we said, remember, when you lose an electron, you're forming a cation, or a positively charged ion. So how much energy would it take for this atom to turn into a positive ion? That's what that term means. So for these guys, if we look at lithium and sodium, we said that atoms are most stable when they have an outer energy level. So for lithium, if I took this one electron off, I would have a really stable ion. I would have something that looked like this. And that's a full outer energy level. So it would have a 1 plus charge, and this would be really stable. So lithium is happy to do that. If I compare that to an atom across the periodic table, if I look at fluorine, this, if I took one off, that wouldn't be very stable. It would still only have 6 electrons in its outer energy level. So, or sorry, yep, 6 electrons total in its outer energy level, 2 in its S and 4 in its P. It's not really happy to do that. It really doesn't want to do that. It would actually be much easier for it to gain 1 electron in order to get that full outer energy level. So it would rather be an anion. It would rather be a negatively charged ion with 1 extra electron. So to take one off, it really doesn't want to do that. And so here, that's going to take a ton of energy in order to get that electron off, because it wants to be there. In fact, it wants to be there with additional electrons too. So when we think about ionization energy, that's going to be pretty easy on this left side of the periodic table. So it's going to be pretty low down here. It's not going to take a ton of energy to take electrons off here. So it's going to be pretty low. And as we move across, these guys really don't want to lose an electron. So it's going to take more energy. That's going to be a higher amount of energy over here. So this is going to go this way, ionization energy. And you may also see it referred to as first ionization energy, and that just means the amount of energy it takes to take off 1 electron. Second ionization energy would be how many it would take off, how much energy it would require to take off 2 electrons. So ionization energy, as we move across the period, it's going to take more energy on the right side of the periodic table than it does on the left. As we move down, now we have to think about shielding. So as we move down the group, from here to here, it's similar to when we were thinking about that atomic radius. So if I compare sodium to lithium, I've got more shielding, which means that this electron isn't feeling this positive charge as strongly as this electron is feeling this positive charge, because this electron is shielded by all of these. Remember, this is like our additional magnet that's kind of blocking that charge. And so for that reason, this isn't being held on to as strongly by the atom. And so it's easier to let go of that, because the same way it would be easier to pull off, if I compare, let's think about our magnets again. So it's going to be easier for me to take away this electron, this is like sodium, than it's going to be for me to take away this electron. So because of that, it's going to take less energy. So my ionization energy is going to be this direction, because it's going to take less energy to take off these electrons than it's going to take off these electrons. So my ionization energy is going to go this direction. All right, so that was ionization energy. Next, we have electron affinity or electronegativity. They are two different things, but we can really kind of think of them in the same way. And they're just how strongly is this atom going to hold on to electrons? How strongly is it going to pull other electrons toward it? And so if we think about fluorine, fluorine has it really wants this one extra electron, so it's gonna kind of work in the opposite way that ionization energy is. It's almost saying, okay, well, how much energy does it take for me to get an electron? If this was to lose one, what about to get one? So this really wants to pull on electrons because it really would be super happy to have just one added electron here. And this wants to lose an electron. It doesn't want to gain one. And so here, this is not going to be happy. So as we move across a period, our electron affinity is going to increase because these guys really want electrons more than they want to lose one. And then as we move down, now we have to think about shielding again. So this guy compared to this guy, they both really want one electron. You want one and you want one, but who wants one more is the question. So here we're thinking about who's going to feel that pull more strongly. Which of these guys, which of these electrons would be pulled on by that nucleus more? And so it's going to be the one that has less shielding because this attraction is going to be felt more strongly than this attraction because we have our additional negative charge in there blocking the attraction between this electron and this nucleus as compared to this guy where we don't have that extra energy shell blocking it. So our electron affinity as we go down a period is going to decrease because there's additional shielding, meaning that we're not going to feel the pull on the electron as strongly as we would when there's less shielding. So here we are going to go this direction, and I'll put it on this side just because we're running out of room on that side. All right, so that was electronegativity or electron affinity. And last, we want to think about reactivity. So reactivity is going to be a little bit weird to think about the trend because it's not going to be the same for everything. It's actually going to be kind of, I'm going to draw it a way that you're not going to see it anywhere else. But when I think about reactivity, I almost think of it as moving out like this. So this is going to be my reactivity. And where can I fit it? And same way here. It's going to kind of move out like this. Sorry, it's a little messy. So really, it's on the extreme ends of the periodic table is where we're going to have the most reactive elements. And what I mean by that, so that's a little confusing, right? Because then we're saying that total opposites are doing the same thing. But really, atoms become more reactive when they're really close to being stable, but not quite, when it would be pretty easy for it to get to stable. So basically, if we think about this guy, he only has to lose one electron in order to get to that full outer energy level. This only has to lose one electron. So these are really reactive elements. So this first column here, these only would have to lose one electron to have one full outer energy level. So they're really, really reactive. Same with these. Oops, sorry, not those. Those are not reactive. These guys are also really, really reactive because they only have to gain one. So if you only have to do a little bit to get to that most stable place, then you're just like, oh, it'd be so easy for me to get there. I only have to do this one little thing. And so these become really reactive. Compare that to, I didn't draw them out, but let's draw oxygen really quick. So this would be here in the periodic table. It would be on this side. I'm going to draw it down here just so I have room. And I'm going to change colors so it's not confusing to look at. That O is the symbol, not one of the rings. And oxygen is going to be 1s2, 2s2, 2p4. So 1, 2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4. So here it would take 2 electrons. So it would have to do a little bit more to get to a full outer energy level. So it's kind of closer to just chilling. It's like, well, if it's going to be hard for me to get there, that would take more energy for me to do that. I have to gain an electron twice. I have to do 2 things. So it's going to take more energy for me to actually do my reaction. So here, this is going to be less reactive. So the way I'll see this trend written is that for metals, your reactivity is going to go like this. As we move further to this side, we are going to be more reactive. And as we move down, and again, this is just because of shielding, so this is going to be more reactive than this, because again, this attraction is not felt as strongly as this attraction because we have that extra layer in there. So same with ionization energy, because it's easier to just bounce that guy off. It's going to be easier for it to do that reaction as well. For nonmetals, it's going to be the exact opposite, because nonmetals are going to want to gain electrons rather than lose electrons. So it's going to be moving in the opposite direction. So it's for the same reasons that we have a higher electronegativity for fluorine than we do for chlorine because of that shielding. As we move up the periodic table, up a group, we're going to have a higher reactivity because it's going to be easier for you to gain that electron. And as we move across, it's going to be more likely for you to want that electron. And so that is why my reactivity for nonmetals is going to go in those 2 directions. And the last piece I want to address is just when we think about our noble gases. These guys already have a full outer energy level. They've already got those 2s electrons and 2p electrons, or whatever energy level we're in. Krypton already has its 4s and its 4p. Xena already has its 5s and its 5p. It's got those 8 electrons in its outer energy level. And so they're already really stable. They really don't want an extra electron. They'd have to make a whole extra shell to put it in. They don't really want that. They don't really want to lose an electron, because then they'd go from stable to unstable, and they're not happy there. And so anything in this noble gas column, not reactive at all. So those guys are totally non-reactive. They're what we call noble gases, and they're called noble because they're too good for anybody else. They don't want to react. They are just chilling. They are happy the way they are. These are all non-reactive. So they kind of break the trend on that one. So they kind of break the other trends as well. Atomic radius, they do fit the trend, but ionization energy, they have a very high ionization energy for all of them, just because they don't want to lose electrons because they're happy with their electrons. Their electron affinity is going to be low all the way throughout because they don't want to attract electrons. So the noble gases, when we think about the trends, the noble gases are kind of in their own world where we kind of ignore them. And if you remember from our previous video that we watched about Mendeleev and discovering the periodic table, they hadn't even discovered these elements at that point because they're so non-reactive that they're not reacting with other stuff. And so they didn't even know that they existed yet. All right, and so that was our last one. And I will also share with you a much cleaner, nicer looking version of this chart that I'll post into modules, but hopefully it makes a little bit more sense now. And then that should give you a good basis as you go through your reading to not be memorizing these, but to try and understand how they work and why they are the way that they are, because then it'll be much easier to remember them.